Hello there, Mr. Sutton here, bringing you this lesson on integration by substitution, indefinite integrals. For this one, we will be finding indefinite integrals of compositions using integration by substitution.
For your warm-up, pause the video and see if you can remember the chain rule for derivatives. Think you've got it? So we're starting with f of g of x, and the derivative of that is going to be f prime of g of x times g prime of x. In other words, the derivative of the outer function with the inner function unchanged times the derivative of that inner function. So what does this have to do with substitution? Integration by substitution basically reverses this and integrates a chain rule. So let's say we're starting with the integral of basically the chain rule here. How do we get back to f of g of x? How do we undo this? So the key to the integration by substitution is the substitution part. Right now, this is a very difficult function to integrate because you have this composition to worry about. But what if you didn't have to worry about this composition? What if this was just f prime of something else, just like f prime of a single letter? And this g prime of x is kind of annoying too. What if that wasn't there? So to solve all these problems, our first step is we're going to assign a letter. Usually we use u to equal the inner function here that we don't really want to look at. So we'll say u equals g of x. So right away, if we wanted to, we could substitute u for g of x and we would have f prime of u. We're not going to do that just yet. There's a few other steps, but that's where we're going with this. Second step, over here in La La Land here, this is kind of a separate area for work. We're going to differentiate our u equals g of x expression. So that's going to give us du equals g prime of x dx. And if you're uncomfortable with doing this, we could just think of this as integrating all of these with respect to some third unknown variable. Like this could be du dt, this could be dx dt, and then multiplying by dt would get rid of those and we would have what was left here. All right, now why did we do this in the first place? Well, our next step is to isolate dx. So we're going to divide both sides by g prime of x, and that'll get dx by itself. Of course, you still might be wondering, why did we do that? Why didn't we just go ahead and substitute u in here and just be done with it? Well, here's the trouble with integrals when you have two different variables. You can't integrate them. You always have to integrate using the variable of integration here. If this variable of integration is different from the variable in the problem, then the variable in the problem isn't really a variable anymore. It's actually considered a constant if it doesn't match this variable, and we want this to be a variable here. So what we're going to do now to fix all of these problems is a whole bunch of substitutions. We are going to substitute u for g of x, just like we promised, and we're also going to substitute this du over g prime of x expression for dx. So let's go ahead and do that now. So now we have f prime of u, like you've been waiting for the last minute and a half. And then now this, instead of dx, we've got du over g prime of x. So this letter here, the u in du, matches the u over here, and this is a good thing. But wait, you say, we still have this x term here. But look what we have in the denominator. We have another g prime of x. So you guessed it, our next step is going to be to cancel those g prime of x's. And all of a sudden, we're integrating something that looks a whole lot nicer than what we started with. So at this point, now that our variables match, we can go ahead and integrate with u. Well, what is the antiderivative of f prime of u? Why, it's f of u plus c. Can't forget the constant. Now, if they wanted us to actually express our answer in terms of x, we could do this. If you want, we can actually substitute g of x, which equals u, back in for u. So we could write this as f of g of x plus c. So there it is. We've undone a chain rule. I know that was a lot to go through, but we're going to do it again now with an actual function that isn't just an f or a g. Let's do an example with an actual function in it now. And the hardest part about using integration by substitution for a lot of students is realizing that they can use it on a problem. the key to recognizing the situation, knowing that you can use substitution, is if you see an inner function and its derivative in the same problem. So for here, we have an x to the fourth inside another function, so this is an inner function of x to the fourth, and we notice that outside here, we have an x to the third. Well, we know that when we take the derivative of x to the fourth, we get something with an x cubed. So this keys us into the fact that we can use substitution. So we'll start by letting negative 4x to the fourth minus 1, the inner function, equal u. Then we can take the derivative of both sides. That'll be du equals negative 16x to the third. And then we'll isolate dx. So we'll have du over negative 16x cubed. So substituting back in, we'll have negative 80x cubed times u to the negative fifth. And this dx can't stay because the x doesn't match the u that we just substituted. So we have to replace the dx with du over negative 16x cubed. At this point in the problem, after you've substituted the du over whatever expression back in, this is where your x's need to cancel out. You need to get rid of all the variables that are not used at this point. The x cubes are going to cancel completely, and negative 80 over negative 16 as a bonus is the nice round number of 5. At this point, when we have only u's left, we can integrate like we normally would. So bumping this up to a negative 4, dividing by negative 4, we can write this as negative 5 over 4 u to the negative fourth power plus c, because this is an indefinite integral. We're not quite done, though. If we want this to be expressed in terms of x, which is what they asked for in the original problem, we can substitute negative 4x to the fourth minus 1 back in for u right here. And now this is our final answer. We're going to do another example, and in a moment I'm going to cut you loose to try this one on your own. Before we do that, though, let's make sure we pick a good u value, because this makes the difference between getting it done quickly and just pulling your hair out in frustration. Those are really the only two options with substitution. So what should we pick? 2x squared minus 1? Or should we use this entire cube root function with this inside of it as our u value? Well, let's consider our options. If we take the derivative of just 2x squared minus 1, that'll give us an expression with an x that will neatly cancel out this x up here. If we use instead this whole cube root function, the derivative of that gnarly expression is going to give us a chain rule. The tail of the chain is going to have an x in it that'll cancel out this x. But what about the first part of the chain? You're going to end up with some other root with a bunch of stuff with x's in it. So really, letting u be the simpler of the two expressions is the way to go here. In general, you should let u be as simple of an expression as possible. If u generates a chain rule, chances are you're trying to do too much at once. All right, now pause the video and go ahead and finish this one on your own. All right, let's see if we came up with the same thing. Derivative of our u expression, we'll have du equals 4x dx. Dividing by 4x, we've got du over 4x. Substituting back over here, we're going to write the integral of x over cube root of u times du over 4x. And now the x's are going to cancel, so we have a du over 4. Just to make this a little easier to write, I'm going to use, or easier to integrate, I'm going to use a negative fractional exponent, and I'm going to put a constant fraction out in front. So I'm going to write this as 1/4, because we're over 4, times u to the negative 1/3 power. And this is very easy now, well, not very easy, but at least easier than all this garbage, to integrate using our reverse power rule. So we can bump this up, have to add 3 over 3 to it, so bump this up to 2/3, and that means we're going to divide by 2/3, which is really the same as multiplying by 3/2. So that's going to be 3 over 8 u to the 2/3 power du. And now we just substitute back in the 2x squared minus 1, and we're done. And of course, don't forget your plus c in this process. Here's another problem. This one's a little bit tricky. Here we have a cosine and a sine in the same integrand, And the problem here is that they are derivatives of each other. So no matter which one you let u equal, you potentially get something that could cancel out the other function. So does it matter which one we choose? Actually, it matters a great deal. We're going to go with cosine because cosine is an inner function. And it would be very helpful, instead of writing cosine to the fifth power, it would be very helpful to just write u to the fifth power. So we're going to let u equal cosine. And then go ahead and finish the rest of this one on your own if you didn't already. So the derivative of u is going to be du equals negative sine of x, dx, and then divide by negative sine. Subbing back in, we've got u to the fifth power times sine times du over negative sine. Sines are going to cancel, so this is just negative u to the fifth. Bumping that up to a 6 and dividing by 6, we have negative 1 over 6 u to the sixth plus c. And then we'll just substitute cosine back in. So this is negative 1 over 6 cosine 6 power of x plus c. So that's it for the indefinite integral side of integration by substitution. Till next time, Mr. Sutton signing off.